I'm going to start off with a review specifically about what transfer functions are. We're going to talk about how to find them. There's 4 different types of notation, which has a bearing on today's lesson, what the poles and zeros are given a transfer function, and also how to plot them in MATLAB. And then last, we'll review how to find a frequency response, that h of e to the j omega, given your h of z. Next objective is also going to be a review. It's how to find your output given your input and your transfer function. And we've talked about ways other than just simply convolving them. And then we're going to talk about the geometrical interpretation of h of z. How cool would it be just to look at a plot of where the poles and zeros are and instantly be able to tell if that's a low pass filter you're looking at, a high pass, or something else. I'll show you how to do that today. And then the very last thing we'll talk about is different ways to determine if your system is bibostable, so bibostability. Let's begin by talking about this transfer function review. I've got a handout here, and this is an outline of what we're going to talk about today too. The first thing is, how do you find this transfer function, h of e to the j omega, given an impulse response, given a difference equation, given a block diagram, or given actual filter specifications? So let's go through each of those. So the first is how to find the transfer function given its impulse response. And of course, that's going to somewhat depend upon what type of impulse response you're given. There's 2 basic types. What do we call it if it's finite length? Jacob?
If it's finite length, are you talking about the symmetry?
No, although there is often symmetry, but what I'm talking about is that there's a special name we give to a system that has a finite length impulse response.
Periodic?
No, if it's finite length, it can't be periodic. Periodic would always be infinitely long. I think you're still thinking about symmetry.
I'm a little confused.
Well, it's almost a unfair question because it's so obvious. We talked about it just last class. We call them finite impulse response filters. And then the other kind are infinite impulse response filters. And if it's a finite impulse response filter, in other words, if it looks something like that, where this is our 0, then, Jake, just finishing you up, how would you convert this picture to an h of n?
To sum a bunch of impulses.
Just a sum of a bunch of impulses. So this particular one would have an impulse at 0, and then you'd subtract an impulse at 1, and that's its entire impulse response. So this has an impulse response that fires at 0, and then from it you subtract an impulse response that's delayed by 1. If I plugged in numbers in here, then this whole thing would just be a number and it would not be a function. Okay, and then once we have our h of n, then Tim, how would you change that h of n to our h of e to the j omega to find that transfer function?
You use your tables?
Yeah, exactly. Just use tables. Now, for this particular one, it's pretty easy, right? You're going to convert that to an h of z using tables. And let's give an example. Tim, just finishing it up. What is the transfer function of this guy? What's h of z using this one? You may not even need tables. You may be able just to recognize it.
What's h of z using?
Just by looking at it. We've got an impulse at n minus an impulse at n minus 1. Do you remember what h of z is? What the transform is of an impulse?
Is it 1 over z?
Almost. It's transfer function for this one, h of z, is 1. The transform of an impulse is 1. And then this is 1, but it's been delayed by 1. So that's 1 over z. Z to the negative 1. Okay. Actually, the same thing works for IR. If it's an IR, I'd have to give you a function, something like, I don't know, u of n. And then your h of z for that, you'd look up in your tables, and that would be 1 over 1 minus z to the negative 1. And then whatever the case is, you could then convert our h of z to our h of e to the j omega just by letting your z equal e to the j omega. And now you've got your transfer function. So that's a review of how to find your transfer function given an impulse response. How would you find it given a difference equation? An example of a difference equation is something like x of n minus 1/2 x of n equals y of n plus 3/4 y of n minus 2. So you're given the difference equation. How do you find the transfer function? JT?
Would you put like terms together and then...
After you do one thing. Like terms together after one thing. Oh, shoot.
Solve...
Oh, you're right. I didn't. Let me do that. X of n minus 1. Yeah, you're right. Otherwise, you should just simply combine those. I agree. You got to do, we can't put these x of n's together because this is x of n and this is x of n minus 1. So what do we have to do to it to allow us to combine those x terms?
You'd have to transform it into a z.
Exactly. So you transform it to a z, and then you get x of z's. And this first one would be just x of z. This would be minus 1/2 z to the negative 1 times x of z. And then over here, just as you said, JT, this would be a z minus 2, since we're delaying it by 2. And now we can find our h of z by dividing through. And h of z is always going to be equal to our y over our x. So that would give us 1 minus 1/2 z to the negative 1 over 1 plus 3/4 z to the negative 2. And then from there, it would be the exact same as what we did above. Now we've got our h of z. We just replace our z with a e to the j omega, and we get our h of e to the j omega. How do we do it if we have block diagrams?
Don't we just turn it into the differential equation?
That's it. Actually, there's even a faster way. If you don't have negative feedback, you're right. You can write out the difference equation right from the block diagram. But if you've got negative feedback, you often can't do that, especially if there's multiple parts of negative feedback. But there's something you can do to the block diagram first, which makes it all easy. What's that first step that you do? Hint, it's the same thing you did with that difference equation, your first step. John Smith, we have a block diagram. We want to find its transfer function. What's the first step we do?
I was gonna say put it in the z domain.
Absolutely. That's it exactly. Take that z transform. Now you've still got your block diagram. Still looks like a block diagram, but now delays are z to the negative 1s. And then once you do that rule about making sure that there are variables at the output of every summer, and then you create an equation by summing around the summer, and then you'll have the exact right number of equations to either eliminate extra variables if you've got them and end up having a relationship of x of z and y of z, and then from there you can divide the two to get h of z, and then it's exactly the same as what we've been doing before. There's one other way, radically different way that you can get a transfer function, and that's going to be from a filter specification. That was in our handout last class, where if you're given a specification of where you want your omega stop, your omega pass bands, I gave a set of pre-made, pre-chewed equations that lets you create a zeroth order, so n equals 0, m equals 3, finite impulse response that has exactly 3 coefficients, and it's a set of equations that just spits it right out. That's the handout from last class.
Did you say m equals 3 or m equals 2?
You're right. You're exactly right. You're exactly right. It was n equals 0, m equals 2. So there are 3 coefficients. Thank you. You're exactly right. Okay. So that's how to find, that's 4 different ways to find transfer functions.